So last time we had done our apparatuses, and we had started talking about separation of substances. ठीक है, how to separate mixtures. तो उसका थोड़ा सा ना just a brief recap of what we did. Uh, Okay, separation techniques. You've got mixtures. Mixtures are substances that are physically mixed together, and they're not chemically combined. Which means that when something gets chemically combined, their properties kind of change. And for example, H2 is a gas, O2 is a gas, and together they form H2O, which is a completely different thing. So substances are not being chemically combined; they're only physically being mixed together. Uh, So one example was sand and water. So even in a mixture, the properties they retain their properties. Water is still water, sand is still sand, even if they are mixed together. So then we started off with the first mixture, which was an insoluble solid plus a solvent. An example was sand and water. Now in sand and water, what you did was you had so in sand and water you had the first process was decanting. In it, what you do is that if you have sand and water, you just allow it to you wait for a little while, and you allow all the sand particles to settle at the bottom like this. Okay, for example, if you have muddy water, all the sand particles would settle at the bottom, and you can pour off the water from the top. That's decanting. Another one was filtration. You can simply filter the thing out. So you've got because insoluble particles are large, so the sand particles would be stuck in this filter paper, and the thing that passes through it, that's called your filtrate, and that's the thing that's left at the inside the filter paper, that's your residue. Then you have suspensions. Uh, Now that's the third method. Suspensions were when the particles are really, really fine, but they're still insoluble. So that means the particles are not settling at the bottom, and you want them to quickly settle at the bottom. For example, you've got muddy water, and the mud or the sand in it is taking its time to settle at the bottom. So you can speed up the process by a process that's called centrifuging. You can spin it vigorously. You can spin the water vigorously, and just like if you're sitting in a car and the car is turning and you go on one side, all the particles, because you're spinning it, all the large particles of the solute, they end up at the bottom, or they get pushed to one side, and in that way you can sort of pour the liquid from the top. So you can do centrifug. Walaikum salam. Turan, can you hear me?
Yes, sir.
So you've got centrifuging. That's for suspensions. Now let's move to the next mixture, which is what if the substance is soluble? So you've got a soluble solute, so anything that's soluble plus a solvent. So one example is, like, if you have a soluble solute plus a solvent, one example for that is you have I mean that's your normal table salt with water. That's NaCl plus water. That's one example. So NaCl plus water, that's an example. Now the thing with uh, with substances that are soluble is that they get mixed, but they get mixed at the molecular level, which means that even the tiniest atom and the tiniest molecule is going to be, like, if you have NaCl mixed in water, then the particles completely get submerged or mixed. They get completely scattered in water. Like every atom of sodium, it's usually an ion form. Okay, we're going to talk about that later on. So every sodium ion and every Cl ion is separate, and they're all scattered, and they're all completely surrounded by water molecule. That's when you know the substance is soluble. When it has completely and finally, right at the atomic level, it has completely mixed with water. These green ones are your water molecules. So that never happens with sand. Like in sand, the particles are still really, really big, which means they're not scattering, or they're not dissolving at the atomic or the molecular level. So we call a substance soluble if the substance mixes with water right at the atomic level, at the smallest possible level. It's completely mixed with water. So that is exactly what happens when you add those white crystals of NaCl and you mix it in water. The particles completely mix, and every atom, every ion is separate. It's completely scattered in water. So that's what soluble means. Insoluble means that you got very, very large particles, and they're not scattering, they're not mixing with water, at least not at the right at the smallest atomic level. Okay, so that means the substance is insoluble. Soluble is when it is completely finely right at the atomic level, at the level that you can't even see. The substance is completely mixed with water. Okay, is this point clear? Ron, is this clear? Achida, is this clear? Adil?
Yes.
Acha, now what happens in this case? How do you? What are the different methods of separating these substances? Uh, I mean, there's several methods. Like if you, and I'm going to take the example of NaCl plus H2O. So NaCl plus H2O, how would you separate them? Can anyone tell me one method of separation? If you have a salt that's mixed, you can't filter this, because remember the particles that are so finely divided, they're so finely scattered in water that and they're so small, they're so tiny that they can easily pass through a filter paper. You need large particles that get stuck in the filter paper, so you can't really do filtration. So can anyone tell me what you could do to separate the salt and the water? Anyone? Amna?
Evaporation to dryness.
Okay, so the first one is you just evaporate the water, get rid of the water. So evaporation to dryness. So what you're going to do is take an evaporating dish. So let's say uh, this. One second. It's just so you. Okay, you take this evaporating dish and you heat it strongly, and all the water eventually evaporates. So all the water is going to evaporate. Water has a lower boiling point. I mean, it has a boiling point of 100. So all the water evaporates, and the salt is left behind. You can even try this at your home. The salt would be left behind. Now, the problem with this method is that although the salt is left behind, but the crystals are not going to be formed. I mean, large crystals are not formed. So I'm going to explain that if you heat it strongly and you evaporate it very quickly, this is what's going to happen. Like, for example, over here, uh, let me just copy paste this. Sorry. So this is what's going to happen. That if you get rid of the water vapors, water very quickly, all the water would gain energy and they're going to escape. So all the water molecules, they become energetic, the boiling point is reached, and they would escape very, very quickly, and they would leave the container. And the salt would eventually, let's just quickly get rid of all the water. So all the water molecules, they've turned into gas. But since you're doing it so fast that the crystals are not going to be formed, because the ions or the particles, they don't have enough time to get together. So what you're going to get is, I mean, all the water is gone now. So what you're going to get is just a powdered form or just tiny particles. No large crystals would be formed because you're doing it very quickly. Uh, so if you want the crystals to form, uh, so evaporation to dryness is going to give you some powdery substance at the bottom, and because things happen very quickly, the particles don't get enough time to sort of join up and form that substance back again. Plus, there would be impurities as well. For example, if your original water had sand particles, then the salt that you have would still have impurities. So it's not a good method, because and the reason it's not a good method is that one is crystals are not formed, and the other one is uh, impurities. If there are any impurities present, like sand in water, they are not removed this way. So a better method is crystallization, which is kind of similar. That's a but it's a better method. What happens in crystallization is that's number two. Let's talk about that. So we're going to talk about crystallization. I said on crystallization, what you're going to do is you take the same salt and water solution and you have these molecules. The salt is completely mixed. Now you're not going to evaporate all the water. Okay, you're not going to do the first thing. You're not going to strongly heat it and evaporate it to dryness. What you're going to do is instead remove some of the water molecules. Okay, just do a little bit of evaporation, but leave some of the water molecules behind so that there's still some solution left. Once the water molecules are gone, most of them are gone, but there's still some left. The particles which were previously separated or completely scattered, they might sort of try and get together. I mean, you allow it to cool down. Okay, don't get rid of all the water molecules, but get rid of at least half or more than half of the water molecules, so that I mean, previously, why were the particles not getting together? Because there were too many water molecules in the way, and the water molecules were blocking the sodium and the Cl ions to get together to form the crystal back again. Now, what's going to happen is you're not going to remove all the water quickly. You're going to just evaporate it very slightly so that the amount of water is left and the solution is very, very concentrated. That would allow the sodium ions and the Cl ions to get back together again. You sort of give them time, you cool them, and eventually crystals would form. So the particles would find each other and they would sort of get together and crystals are going to form. So that's the major difference between evaporation to dryness. In evaporation to dryness, you just evaporate all the water very quickly, and the particles just don't get enough time to get together. Now, what you do is you just do it a little bit slowly, and you don't get rid of all the water molecules. Okay, is this point clear? Salama, Asida, Adil.
Yes, sir.
Yes.
Okay.
Yes.
So that is crystallization. And remember, you'll be asked a lot about crystallization. A lot of times, almost every second process would have, I mean, at the end, you'll be crystallizing things. So remember the steps of crystallization. Remember, I told you that don't write things in your own words. I mean, you can, because it's chemistry, this is, I mean, you can't just write an essay on things. Okay, so the process of crystallization, it has to be very specific, very brief, use as minimum as possible words to describe that. So this one is going to be that you evaporate. The first line would be, I mean, if you want to describe crystallization, evaporate the solution. And remember to memorize this. So this usually carries 1 or 2 or 3 marks in a lot of questions. So evaporate the solution to saturation point or crystallization point. Let's call it crystallization point. This is the point when the amount of water is so little that the particles can sort of join up and they can form crystals. So evaporate and get rid of the water, some of the water, and evaporate the solution to crystallization point. And then you let it cool. You give it time. Cool gradually and wait and allow the crystals to form. Now, the thing with crystals, with forming crystals, is that the crystals are going to be pure. Because if there are sand particles or there are some impurities in the water, they would not be part of the crystallization process. The ions would get together, but so you can sort of get rid of the impurities as well once you take out the crystal. I mean, a crystal is going to be a huge thing. You can just pick it up with your hand. So in that way, it's going to be a very, very pure. Crystals are always very pure. So cool gradually, allow crystals to form. Once they are formed, you filter out the crystals. And plus, what you're going to do is you're going to dry the crystals because you can't wash them because they're soluble. NaCl is soluble, so you can't really clean them up. What you can do is you can dry them between filter papers. I mean, filter papers are like tissue paper, so you can put those crystals. So dry them between filter papers. Uh, so you just place them in those filter papers like tissue paper, so they can soak in all the liquid that's on those crystals, and the crystals can be dried in this way. So remember the process of crystallization, and whenever you're asked to write the process of crystallization, which you're going to be told very often to write the process of crystallization, use the same words and be very brief. We will be very very specific. ठीक है, क्लियर है सारों को ये?
Yes, sir.
अच्छा चलो ठीक है. Saneem, is this clear?
Yes.
अच्छा, number. So just remember, you can evaporate to dryness, and you can obviously crystallize. Okay, crystallization is better. Can anyone tell me a third way of separating salt and water? Any idea? I mean, there are two more ways actually.
Distillation maybe.
Distillation.
Okay, so the third one is distillation. I mean, this is known as simple distillation. Now, simple distillation is I mean, that's mainly for obtaining water. I'll just copy a diagram of simple distillation. You can just give me 1 second. So, which one? And this looks simple. Achha, so this one. So this is a simple distillation apparatus, and you're going to have your, let's say this is a round bottom flask. Remember, I told you the round bottom flask is for heating. You will be heating the substance over here. And let's say this round bottom flask contains salt and water. So these are your salt NaCl particles. And they are all mixed in water. So this is NaCl plus H2O. And what would happen is that once you start heating, only the water would evaporate because NaCl has a pretty high melting point or boiling point, so that nothing would happen to it. So once you start heating, the water vapors would rise and they would enter this condenser. So this one is your condenser. I mean, you can simply call it a condenser. It's a Liebig condenser. And you might be asked, how does the condenser work? It basically cold water. I mean, it's written, but it's not clear. So cold water is, remember, cold water enters through the bottom opening and leaves, because you'll be asked to label this, and it leaves the top from the top. So it cools things down. So when those particles they reach the Liebig condenser, they're going to lose energy and they condense. So this is what happens over here. Particles lose energy and condense. And this is at the other end. This is where you're going to get water, right? I'm assuming we're distilling NaCl and water. I mean, that was our example. Now, a few more things about this, and those few things are that this container must be I mean, this diagram is slightly wrong, uh, because this container should have an opening as well. I mean, it should have an opening because there's hot gases that are coming in. So you don't want, I mean, not, I mean, assuming that not all the water molecules are actually condensing, there would be a few water molecules that are not condensing. So there's a constant there are constant gases or water vapors that are coming in. So you don't want the apparatus to explode. You don't want the pressure to build up inside it. So also remember that the container, the receiving flask over here, whatever that is, usually it's a beaker or a conical flask, the container should have an opening. It should have an opening so that does not increase. So the pressure does not rise as hot gases they keep coming in. Okay, that's uh, one important thing. So you don't want this whatever this is, that should have an opening. Okay, is this clear? Simple distillation. ये clear है सारों को?
Yes.
As the next one, and remember, sticking to salt and water. There's a fourth method. Okay, and this one is good for actually collecting water. If you want water, and it's good for collecting water, it's good for collecting very pure water. So this is going to be a very, very pure distilled water. The salt would probably not be. It's not a good method for collecting salt. Okay, it's a good method for collecting the water, and I'm going to write that. Okay, so if you're looking for like the previous methods, in crystallization, the water would still have a lot of impurities. The crystal would be pure, but the water is not going to be. I mean, you're not going to get good quality water in this way. Same with, I mean, evaporation to dryness, you're going to lose all the water. So I mean, you're not collecting the water. Same with pretty much all the other methods. Distillation is the one where you get. It's good for collecting the solvent. So good for collecting pure solvent. So let's move to number 4. Number 4 is again about purifying water. So and that is has something to do with air and water. That's the topic that you're going to study right somewhere at the end. That's known as reverse osmosis, or we can also call that desalination. So especially in coastal cities, you want pure water, and the water has a lot of salt dissolved in it. So what happens in that case is that reverse osmosis or desalination is that they pump salt water or seawater at high pressures. So, for example, there's this seawater that contains high salt quantity, and it's pumped at high pressures. And in the middle somewhere, there are these finely meshed membranes, the fine meshes which are really really fine, much finer than filter papers. Okay, that's known as a semi-permeable membrane. So filter papers are good for stopping large particles, but semi-permeable membranes are like really, really. They've got really. I mean, they can stop really small particles at the atomic level, the ones that you can't see. So you have all these salt particles coming in. Okay, these are your salt particles coming in, along with the water. Now, the salt particles would not be able to cross the semi-permeable membrane. So on the other side, you're going to just have pure water, or at least most of the salt particles would stay behind. Very few salt particles would actually be able to pass to the other side. So that's how seawater is converted into pure drinkable water, because you've got semi-permeable membranes, which stops the microscopic. They're not even microscopic. They're at the nanoscale, so they're even tinier than that. Stops tiny salt particles. So that's how desalination works, especially in coastal cities. ठीक है, so is this clear as well?
Yes, sir.
So then you have the next one, which is so remember four ways: evaporation to dryness. You've got crystallization. You've got simple distillation, and you've got reverse osmosis. Uh, and this is specifically, I mean, you're going to be talking about this, especially in air and water, when they'll ask you about how water gets purified. The next one, or the next mixture that we're going to talk about, is uh, two miscible liquids. So what if you have two miscible liquids? Now, two miscible liquids, that what that basically means is that they're basically two solvents that, or two liquids that completely mix with each other. Two liquids soluble in each other. So one of the examples for that is, how do you separate two miscible liquids? One example is ethanol plus water. So any idea how to separate ethanol and water?
Fractional
Fractional
distillation.
distillation.
TK, exactly. So that's going to be fractional distillation. And the property that fractional distillation, so you'll be asked what property is used to separate them. The property that's used is that they have different boiling points. You've got 78 degrees centigrade, water boils at 100 degree centigrade. So fractional distillation would only work if the two liquids are going to have different boiling points. So so it requires, or we can say that separation happens because of different boiling points. Because of I said different boiling points. So fractional distillation apparatus. Just let me quickly uh, let's draw it ourselves. Okay, so I've got a round bottom flask. This is where I'm going to heat the mixture. Now on top of that, there's going to be. I mean, this is like distillation. Okay, let me write that we're using fractional distillation. So everything is kind of the same, except that there's going to be a fractionating column. The fractionating column is that there's going to be in the center. There's going to be uh, in the center. There's going to be a probably just a column that would be known as the fractionating column. Just a second. Okay, so there's going to be a column that's known as a fractionating column, and then there's going to be a condenser that's going to be attached to it. So that's our opening, and we will have. I mean, let's see. So that's our condenser. तो ठीक है काफी. अच्छा, this is how the apparatus would look like, and that's your condenser. इसके ऊपर मैं let me draw the water in and water out. So this is your cold water going in, and that's your cold water coming out. Okay, so everything is pretty much the same, and there's going to be a container, and remember the container should have it should have I mean, it should be open. It shouldn't be closed. Now, this fractionating column over here contains, or it has a large surface area. Now, that large surface area could be made by adding glass beads so that particles have lots of things to collide with. Okay, so that increases the surface area. So there would be a lot of surfaces to collide with it. So you can add glass beads to it, but you can do a lot of things to increase the surface area. You just want the particles to have more collisions. At the bottom, you have ethanol. And you have water, the mixture of ethanol and water. And you'll be heating that mixture at the bottom. Okay, so the mixture would be heated. As a first thing, who's going to evaporate first, ethanol or water? I mean, I did.
Ethanol.
Ethanol.
Okay, so it's going to be ethanol, 78 degrees centigrade, and this is 100 degrees centigrade. So ethanol would start to boil or evaporate, and you would start seeing, let's say, these green particles. These are your ethanol molecules that have gained energy, and they've turned into gas, and they are now traveling upwards. So ethanol is evaporating, and ethanol particles are going to travel, and they're going to travel, and they're going to bump with all the. I mean, let's say this ethanol molecule would travel and would eventually bump with a lot of your glass beads, and would keep traveling. Then would enter the condenser, and over here it's going to change into gas, into liquid. Sorry, and once it's in liquid state, it would condense and turn and fall down as a drop of liquid, right? So that's what's happening to ethanol. Would water also evaporate when ethanol is boiling?
Yes.
Okay, remember earlier when we were discussing kinetic particle theory, and this is the, I mean, usually you're given a graph as well in these questions. So that's your temperature graph. So the temperature is going to go like this. When you start heating it, the temperature would immediately start to increase, but it would become eventually constant. It's going to become constant at 78 degrees centigrade. That's when ethanol starts to boil, which means that ethanol has started to change state, and it is now in gaseous form, and it's now moving up and reaching the other side. So eventually you're going to get, at 78 you're going to get a lot of ethanol molecules at the other side, and that's your distillate. So a lot of ethanol molecules would start falling in, they would evaporate and condense in the beaker, in the Liebig condenser over here. But the thing is, I told you that evaporation, like boiling happens. I mean, there's a tiny difference between boiling and evaporation. Boiling is when the whole substance starts to change state. So at 78, ethanol would actually be changing state. I mean, it's going to be changing state. And the whole of ethanol would be evaporating, and you'll be condensing it, and you'll be getting it at the other end. But what's going to happen is that at 78, some of the water molecules at the surface would also try to escape into gaseous form. They would become energetic, and they would turn into gas as well, even though it's not their boiling point. But evaporation can happen at any temperature. You throw water on the floor, then the water at the top surface would start to gain energy from collisions within itself, and they would evaporate. So you want, like when ethanol is condensing, you don't want these particles over here, the pink ones over here. you don't want these particles to reach the other side. I mean, this particle would also bump and might reach the other side. You don't want the water molecules to be over here because you're trying to separate them. So the glass beads, they help over here because if the pink particle, the water molecule, it reaches this, because of the frequent collisions with the glass beads and because of the large surface area, the water molecules are going to lose energy. They're going to lose kinetic energy, they're going to lose speed, and eventually they would turn back into liquid and they would fall back into the container. So the glass beads are like a barrier. Uh, they allow ethanol to evaporate and pass through them because ethanol at 78 degrees centigrade, it is in gaseous state. So ethanol would not condense at 78. But the water molecules, the few water molecules that manage to actually escape, uh, they would lose energy. And because it's not even water's boiling point, those molecules would quickly condense and fall back. So only ethanol would reach at the other side. So you'll be asked about the fractionating column a lot. So, so I'll just mention what the fractionating column does, and the answer to that question is the answer to that question is that, again, be very specific. It increases surface area and doesn't allow the higher boiling point liquid to reach the condenser. So, so this is the purpose of the fractionating column. Uh, and why does that happen? Because a large surface area, you have more collisions. The molecules are going to have more collisions. And because of that, they lose energy and they condense. And they condense back. So you'll be asked about fractionating columns a lot, especially when you get questions on distillation. Plus, also remember that there's going to be a thermometer that's going to be placed. That thermometer is very, very important because that tells you exactly. The thermometer is always placed at the opening of the condenser because that exactly tells you what's going into the condenser and which substance is getting condensed. So if the temperature is stuck at 78, I mean, this is the graph of the thermometer, that means ethanol is boiling and ethanol is being collected. Once all the ethanol is gone from the mixture over here, then it's water's turn. So the temperature would start to rise again because all the ethanol is gone. And then the temperature would become constant again at 100 degrees centigrade because that's the point when water would start to boil. And as long as water is boiling, the temperature would not increase. But as soon as all of the water has boiled, the temperature would start to increase above 100. So remember, as long as a change of state is happening, the temperature pretty much remains constant. ठीक है, ये clear है सारों को? ठीक है, is this clear?
Yes, sir.
Yes.
तो बस ठीक है, ये two miscible liquids कर लिया है. We'll probably just quickly end this tomorrow then. ठीक है, फिर we'll start past paper questions. चलिए ठीक है, कोई question नहीं है किसी का? क्लियर है? तो कल फिर कंटिन्यू करते हैं. ठीक है, ओके देन एवरीवन, टेक केयर, अल्लाह हाफिज़.